So people remember reinforce. Remember reinforce? So remember what we did with reinforce. Anyone can give me the update rule for reinforce? Now people are wondering why did we nod? So all of you remember reinforce, right? So give me the update rule for reinforce. The change in theta will be oh yeah, I use t, right? N. Okay. Rn minus huh? Do?
Characteristic eligibility ln pi an theta
An. Yeah.
an theta n.
Yeah. An theta n. So this is the update equation, right? Correct? So what was this guy? Reinforcement baseline. And we looked at one example of using this baseline. Did we talk about an example for what this baseline would be? We did talk about it being the average of all the previous rewards, right? So and what was the thing I said? So Bn is kind of the average of all the previous rewards, and if Rn is above Bn, then it is a good action. If Rn is below Bn, then it is a bad action. Right? We said that Bn is a baseline. Right? I took it as the average of everything that went on before it. Right? Suppose I want to extend this idea to the full RL problem. Suppose I want to extend this idea of a reinforcement baseline to the full RL problem. So how will I do it? Huh?
Make it as a value function of the state.
Make it as a function of the state, right? Instead of having it as Bn, right? I will probably make it as Bn of S, right? And what will Rn become?
Return.
Return from that.
Return, right? Right. So, right. So it has to become the return starting from S, right? Well, whatever, yeah. Right, so something like this you will start getting, right? Right, should it be the return? Can it be something else? Okay, we will come to that, okay. So this is essentially what I am going to look at, right? So what is this guy? Huh? Huh? Exactly. Can you define it before you say it's a value function? What is it? What would it be in words? Generalizing from Bn. What was Bn? The average of all the rewards that you would get from that place. So what should Bn of Sn be? The average of all the returns you should get starting from Sn. What is that? That's the definition of value function, right? So if I extend this reinforcement baseline idea to this, I essentially end up getting a value function, right? But then nothing else has changed. I am still solving for the what? Policy parameters. But I am still solving for the policy parameters, but in the evaluation I am using a value function. Right? I am still solving for the policy parameters, but in the evaluation I am using a value function. So this kind of generalization of the reinforcement comparison idea to the full RL problem suddenly gives rise to both a policy as well as a value function, right. So this is my critic, this is my actor. So the theta gives me actor and the value function gives me critic. So this kind of a generalization of the basic idea of policy parameterization gives rise to actor critic, right. So, that is one way of thinking about what actor critic is, correct. So, I can replace this Gn with what? Right. What is that? A TD error, right. So, this term somehow magically became a TD error, right. So, if you think about what is happening with your critic updates, I mean sorry the actor updates, it becomes some alpha times TD error times this gradient, right, and depending on how you choose the policy parameterization, this gradient can also vanish. What would be the policy parameterization so that this gradient term goes away?
Softmax.
Softmax will make the gradient term go away.
Some exponential. No.
Some kind of a lookup table kind of a representation for this, right. I mean it is not a softmax kind of thing. It's a, I can think of a lookup table like think if it's 1, if it is that action is taken in that state, it's 0 for everything else, right. So I can look, you remember when we talked about value function approximation, we said we could have indicator variables like parameterization. You could have an indicator variable like parameterization for policies as well, right, in which case you can just write like a TD update rule, right, you will just look like a value function update rule, right. So it will essentially delta t will start looking like it will start looking like alpha n delta n into some whatever is the phi of Sn, whatever is your state encoding at that point, right. So if you use some kind of linear lookup table like parameterization for it, will be either 1 or 0 depending on what is happening there, right. So this is essentially what you will end up with, right. So this is the updation for the policy parameters. What will be the updation for the value parameters? I have to learn V, right. We already looked at V. So what will be the updation for the value parameters? The TD update rule. So what is the difference between this rule and the TD update rule? People still haven't found out what is wrong with this rule. Nobody has told me this.
No, not
Huh?
You do not know. Huh?
All
Why does 5 figure in the policy update?
What is it?
Why does the 5 figure in the policy update?
I need some kind of parameterization I am using for my policy, right. That is why I say this will be like 1 or 0. Right. So depending on what parameterization, it could be something else also, but if I am using a lookup table like parameterization, this will be 1 or 0. There is something missing here, something big missing here. So I am going to do a lookup table like parameterization. I will need the actions also there, right. So for this state action pair, if it is 1, that means that is the action I am going to do in the state. If it is 0, that is not the action. So it is going to be that, right. So essentially what will happen in this case is that I will do the same update, except that in the actor I will do the update corresponding to that particular action. If I took that action this time, I will change the parameters, otherwise I will not. And for the state case, regardless of that action I take, I will update the value for every action I take, every time I visit the state, right. You understand the difference? So the actor and the critic will always be changed by the same amount, which is alpha n delta n, right. Both of them will get updated by alpha n delta n. The only difference is the critic gets updated, the same parameters get updated for the critic regardless of what action you take. As long as you visit the state, you will update the value function for the state, right. It is common sense. I am just telling you, it just falls out naturally by whatever the framework that we are setting up, okay. And for the actor parameterization, right, the actor corresponding to the action that you took will get updated by alpha n delta n, right. So you have to choose the parameterizations appropriately so that you get that, but that's the basic idea. So this is the basic actor critic method that is actually presented in the book, the edition of the book as it stands now, okay. They don't actually do the function approximation part. So actor critic is presented in the book before the function approximation, right. No, it's actually presented after the function approximation in the second edition of the book, but the text that was written was copy pasted from the first edition. They have not adapted it yet, and in the first edition it appeared before the function approximation chapter. So in the second edition also they do not make reference to function approximation yet, right. So as Rich keeps adding more material to the second edition, that will also change. This is one peril of using a book that is being written, right, as we speak. So chapters are fluid, they may change next week, but right now the version that we downloaded at the beginning of the semester has this inconsistency. It has the same text from the first edition, but in a different part of the textbook, okay. This is roughly, people got what we are doing here, right. Right. The second motivation for actor critic is as follows, or I already told you the second motivation for actor critic. The first motivation is what? We are generalizing from reinforcement comparison, like using a reinforcement based line. If we start using a reinforcement based line per state, then you kind of get into an actor critic kind of a setup, right. So the other motivation for doing actor critic is to go back to policy gradient again and say that, hey, policy gradient has a lot of variance, so we would like to reduce the variance, right, and therefore we, instead of using returns as the evaluation for a policy, I am going to somehow try to bring in the value function, okay. So that is essentially what we are going to see next. How do you bring in the value function in that setting, okay. This will be slightly different motivation for this, right.